Hi, we're the Micrometers, and I'm Kayley Romero.
I'm Lindsey.
I'm Luis Roncal.
I'm Clede.
And I'm Eric Hutchison. This video documents the process of building 3 separate measurement systems and showcases the working prototypes. For this project, we needed to design 3 systems which measured temperature, water level, and distance, and then report the measurements back to the user via a dial indicator or digital display. This slide shows the specs for each system.
The strategies employed for accomplishing our goals involved the following: meeting at least once a week, or, if deemed unnecessary, whenever complicated issues arose; working through the provided lesson plans to gain a better understanding of the Arduino board as well as the coding required; and combining the physical and coded components of our project, troubleshooting as necessary.
The first system we made is the temperature measurement system. This system uses a thermistor to gauge the temperature around it, and this temperature will be displayed on an LCD screen as shown in the picture. To construct this system, we followed lesson 21 for the wiring and used the code given to us. While trying to create this system, we had a few issues with getting the LCD screen to print the temperature on it. We checked our wiring by making sure they were fully secured and kept turning the potentiometer until we got the display we needed.
The distance measurement system we created was used combining the lessons we learned using the servo motor and the distance sensor. We used the 2 codes provided from these 2 lessons and combined them to allow the servo to function as a dial-style display. Some of the problems we ran into with this system was that the max distance of the sensor would run into issues, as it would be the max in the code and would act a little weird. So in order to overcome this problem, we adjusted the code and made the max distance 60 centimeters so it would easily read that 50 centimeters without any hiccups. Another issue we also ran into was the sensor picking up certain objects, and we realized that in order for an accurate reading, we had to use a very big and flat object in order to get those very accurate readings.
The third design we put together was the water level system. Like the distance system, this one would display its output on the dial indicator. The water sensor has a max range of 0 to 4 centimeters, but in practice it's closer to 2.5. A substantial problem we ran into was the non-linearity of the sensor's output values. As you'll see in a few slides, the dial covers more distance for shallower depths than it does when submerged closer to its limit. We attempted to correct the non-linearity, but we couldn't work out a function to do that properly.
For the calibration of the thermometer system, we compared the values the Arduino was receiving to a mercury thermometer. The way we compared the 2 values was by recording the value on the mercury and the Arduino thermometer every 2 minutes for 10 trials. We found the relation between these 2 values by graphing them together.
For calibration of the distance measurement system, we used a tape measure to map out 50 centimeters on a flat level surface. We then placed our distance sensor at the 0 centimeter mark of our tape measure and then proceeded to take measurements for every 5 centimeters from our dial display, and then recording the actual distance measured by the tape measure. To calibrate, we will graph these 2 measurements against each other and see their relation.
The water level system was by far the trickiest to calibrate. The ideal way to do this would have been to include a function similar to the one in a previous slide, but this proved difficult to implement, and only really compounded the sensor's errors. We settled on the method of stretching the scale on the readout to match the servo's output. The sensor was submerged at 5 mm increments from 0 to 2.5 centimeters. At each increment, we marked the corresponding value directly onto the readout. This resulted on a distorted readout, but it was repeatable.
Creating the 3 systems was the main goal of this project, and seeing the working prototypes was pretty satisfying. We could transfer the elements used in this project to create a wide variety of Arduino measurement systems and probably get somewhat complex with it. While this part of the project was cool, there were other important things learned here besides Arduino. One big thing is that it is important to make mistakes on certain aspects of projects like these when it doesn't matter, i.e. before we get to industry. One of those mistakes is not gathering all the data while the systems are still assembled or available. Likely in industry, as an engineer, you won't be able to say, hey, we actually need to rent this equipment again because I forgot to record this data. I'm sure it doesn't work like that, so this will be a good reminder for the future. Because of this, we weren't able to calculate the hysteresis error, which would have been nice to have.